For today's quick quiz, which I'll hold up right now, we'll be talking about a hollow metal ball. This is a ping pong ball and there's aluminum foil wrapped around it. The question that we have for today is if I took a charged rod, and this is just a piece of PVC that you can pick up at Home Depot, and I have some fur here. If I were to rub this rod against this fur, this rod will end up taking electrons from the fur, leaving this as a positive, making this as a negative. The question I have is if this is not charged, I can grab onto it, there's no charge on it, and I were to take a charged rod next to it, what would this ball do? That's our question. Why don't you write your answer down below on your piece of paper? Let's go ahead and try this. First thing I'm going to do is I'm going to end up taking my rod and I'm going to put electrons on. And you'll literally be able to hear them being ripped off. You can hear that there are electrons being ripped off here. In fact, they're jumping to me. If I were to take this next to the uncharged metal ball, you'll see that it attracts and really wants to end up touching this. And once it does, notice it's actually going to start to repel this charged rod. The responses that we normally get for students are three. A, it's not going to do anything. Why would a charged rod do anything to a neutral ball like this? That makes sense. Some will say that, well, maybe it would be attracted for some reason. They can't figure out why, but they think it might be attracted. Almost nobody thinks it's going to be repelled. I don't exactly understand that because if it can attract, it could probably also repel. All right, let's try and provide an explanation of what's happening here. If I have an uncharged rod and I have an uncharged hollow metal sphere, if I take it next to it, we wouldn't expect anything to happen. This is what occurs in our everyday life. However, if I were to put some of the charges on here, which we can hear, and they're making that crackling sound, and I were to take it next to that metal ball, well, there are electrons that are on this charged rod. If you're an electron, you don't like other electrons. On an insulating rod, you're stuck there. You are stuck here, 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 and here. But if you're on the metal ball, metal balls allow, or any metal object allows electrons to flow reasonably freely. Those electrons that were in the ball can end up going to the other side. That's going to leave our positives on the other side. Positives are stuck there. Now, the key to this is that this distance between the positive and the negatives are reasonably small compared to the bigger distance from the negatives to the other negatives. And according to Coulomb's law, the force electric being K electric, Q1, Q2, divided by the distance separating them squared, and it's really that distance separating them squared that's key. Another way to write this is that our force is proportional to our inverse distance squared. Another way to write this is we could say as D increases, the force decreases, and vice versa. So in this particular case, I have an attractive force between the positives and negatives. Smaller d is going to end up being a greater force, and this is going to be greater than the larger distance of the repulsive forces. And therefore, this tug of war is going to be won by the attractive force, and that ball is going to swing to the rod. However, once it swings to the rod and they touch, now I have negatives on the metal side of the ball over here. I have my positives lined up close to the rod. Physically touching allows some of the electrons to jump on board here. What's important to notice is that I have 1, 2, 3, 4, 5, 6 negatives in this representation and only 3 positives. At that point, this ball has a net negative charge. I still have charges on that negative rod, and therefore they are going to feel a force, electrical, that is going to be repulsive. And therefore it's going to try to stay away from the rod at that point. So that's your explanation of this phenomenon.